Hello guys, in this video we are going to discuss the solution of the problem 01 knapsack problem. So let us look at the problem statement. The problem statement says you are given weights and values of items and put these items in a knapsack of capacity W to get the maximum total value in the knapsack. In other words, given two integer arrays val and weight which represent values and weights associated with items respectively. Also given an integer w which represent knapsack capacity, find out the maximum sum value subset of val such that the sum of the weights of the corresponding subset is smaller than or equals to w. You cannot break an item, either pick the complete item or don't pick it up. So for instance, if the knapsack capacity is 4 and value and items are given by these array, then in such case the maximum value which we will be able to fill it in our knapsack is 3, and that is what we are returning over here. So that's about the problem statement, folks. Now let us discuss the solution of this problem. So to discuss the solution of this problem, let us take an example. So let us say the capacity of knapsack is 4 unit and values and weight are given by these arrays. So what we are going to do is we are going to start with a knapsack of capacity 4. Now in this knapsack of capacity 4, what all items can be fit in? So we have 3 items and the weight of these 3 items are 4 unit, 5 unit and 1 unit. So clearly this item will not be able to fit it in this knapsack, so we will not be able to traverse this, but the other 2 items can be fit in. So let us say this is the branch where we are picking item 4 in our knapsack, whereas this is the branch where we are picking item 1 in our knapsack. After filling knapsack with this item, the remaining weight of knapsack or the remaining capacity of knapsack will be 0. Similarly, over here the remaining capacity will be 3. Now as far as this node is concerned, we are done because now we don't have any capacity in the knapsack. But if we take this node, then there is some capacity, and let us say whether we will be able to pick an item over here or not. Now since the remaining capacity is of 3 unit, but the remaining items which are left with us is of unit 4 and 5. Please note, this item is something which we have already consumed. Now since the weight is 4 and 5, so clearly we will not be able to pick any item, because of which these are the only arrangements in which we will be able to fill our knapsack. Now if we follow this arrangement, what is the value which we will get over here? So in this we have filled the knapsack with an item whose value is 1. Please note, corresponding to 4 the value is 1. So over here the value which we are obtaining is 1. Similarly, if we fill this, the value which we will obtain is 3. And since we have to maximize our knapsack value, because of which the maximum between these two is what we are going to pick, and we are going to return 3. Let us take one more example in order to understand this concept. So let us take this example where the knapsack capacity is 5 unit and the value and weight is given by this array. So we have a knapsack of capacity 5 and we have an option to pick any of these weight. Now since all weight are less than 5, so we will be able to serve all these weights. So let us have the transitions as well. Now if we are picking an item whose weight is 1, then the knapsack capacity or the updated knapsack capacity will be 4. Similarly over here it will be 3 and 2. Now if we explore this node further, what we obtain is 4 is the knapsack capacity and we have items of unit 2 and 3, since 1 is something which we have already put in our knapsack. Since 2 and 3 both are less than 4, because of which we will be able to serve both. So 2 and 3, resultant capacity will be 2 and 1. Similarly, let us fill it for these two nodes as well. So when the knapsack capacity is 3, out of 1 and 3, we will be able to serve both, because of which let us have both the transitions. And similarly for the last node as well. And for the last node, since the capacity is 2, so we will be able to serve 1 as well as 2. And the resultant knapsack capacity will be 1 and 0. Now let us proceed forward. For this node, We have already picked item 1 and item 2. The only item which is left is third item, and since 3 is greater than 2, we will not be able to put anything in this knapsack. And the same goes for these nodes as well. So for all these nodes, it is not possible to pick any other element, because of which we are not going to explore it further. Sorry folks, this will be 0. Since over here the capacity available was 3 and we have picked an item of capacity 3, so the resultant should be 0. Now let us proceed forward. So if we analyze this node, then for this node we have already put item with weight 1 and 2 in the knapsack. The only item which is left is this item, and since its weight is 3, which is greater than the capacity, because of which we will not be able to put it in the knapsack. And the same goes for all other nodes as well. And in this way, we have found the possible arrangements in which we will be able to pick items in knapsack. Now for all these arrangements, what we are going to do is we are going to compute value. So the value associated with this is item number 1 and item number 2, and the value will be 8. Similarly for item number 1 and 3, the value will be 12. For 2 and 1, it is 8. 2 and 3, it is 18. 3 and 1, it is 12. 3 and 2, it is 18. And since we have to compute the maximum, so the maximum is 18, and that is what we are going to return. So for this case, we are going to return 18. So as we can see from both the examples, we are breaking the bigger problem into smaller subproblems. We are storing the values of smaller subproblems, and then we are using that value in order to solve the bigger subproblem, which is a classical case of dynamic programming. So the way or the optimal way of solving this problem involves dynamic programming. So we will need a DP table, and the size of this DP table will be numbers of items and capacity of knapsack. So let us discuss the DP approach to solve this problem, and for that let us take this example. So in order to solve this problem, we will need a DP table. So let us take a DP table. So let us say this is the DP table, and the item number 0, item number 1, item number 2 and item number 3. And similarly, let us say knapsack capacity is 0, knapsack capacity is 1, 2, 3, 4, 4, 5 and 6. So when the knapsack capacity is 0, we will not be able to pick any item. So all these values will be 0. Similarly, if there is no item, we will not be able to put any item in the knapsack, because of which all these values are 0. Now, when we have just one item, which is this item, and the capacity of knapsack is 1 unit, then in such case, it is possible to put this item in the knapsack, because of which the value over here will be 10. Similarly, when we have just one item and the knapsack capacity is 2 unit, in that case also it is just possible to put one item which is of value 10. And the same goes for all these cells. Now, when the number of items available to us is 2, which are these two items, in such case, if the capacity of knapsack is 1, then in that case we will just be able to put the first item, which is of unit 10. So let me explain this. So over here, the capacity of knapsack is 1 unit. The items which we have are these two items. Now clearly, of these two items, I will be able to pick only this item, since the capacity is 1, because of which the corresponding value or the value associated with that item will come over here. So this is 10. Now let us solve for this case. So as you can see, this is cell 2, 2. So we want to solve for DP of 2, 2. Now for DP of 2, 2, we will check whether the second item can be served over here or not. Since the capacity of knapsack is 2 and the weight of second item is also 2, because of which we will be able to serve it. So the value associated with that will be 15. Now the number of items we are left with is 1, since we have already consumed one item, and the weight which we are left with is 0, because the weight associated with this item was 2 unit. So as you can see, this problem translates to 15 plus solution of DP of 1, 0. and dp of 1 comma 0 is 0, because of which the value over here will be 15. Similarly, let us solve for dp of 2 comma 3. So since we will be able to solve the second item, since the weight is 2 and the knapsack capacity is 2, because of which 15, and then the subproblems translates to dp of 1 comma 1. Since the weight of this item was 2, so 3 minus 2 equals to 1. So this is 15 plus dp of 1 comma 1, and dp of 1 comma 1 is 10, because of which this value will be equals to 25. And similarly, with the same reasoning, if we follow all these, the values over here will be 25. Now let us look for this case. So we want to solve for dp of 3 comma 1. This simply means we have 3 items and the knapsack capacity is 1 unit. And the 3 items which we have are of unit 1, 2 and 3. So for this problem, as you can see, it is not possible to put item 3 in the knapsack because the weight of item 3 is 3 unit and the knapsack capacity which we have is of 1 unit, because of which the solution of this problem simply translates to dp of 2 comma 1, since it is not possible to put third item into the knapsack. So for this case, the value will be dp of 2 comma 1. And what is the value of 2 comma 1? Well, this is equals to 10. And similarly, we can solve for rest of the items and the values will be 15, 40, 50, 55 and 65. And towards the end, we are going to return this as our answer. So that's the DP approach to solve this problem, folks. Now let us write down the way we will be able to populate our DP table. So let us say we want to populate for entry dp of I comma j, where I is the number of items and j is the capacity of knapsack. So for this, first thing we are going to check is if I equals to 0 or j equals to 0. So if either I is equals to 0 or j is equals to 0, then dp of I comma j will be equals to 0. Otherwise, we are going to check whether the ith item can we put it in the knapsack or not. So for ith item to be put into the knapsack, weight of the ith item should be less than or equals to the capacity of knapsack. So if it is possible to put the ith item into the knapsack, then we are going to put the ith item into the knapsack, and dp of I comma j will be given by maximum of putting the ith item into the knapsack, so value of ith item, plus dp of, now the number of items reduced by 1, so I minus 1, comma, what is the capacity of knapsack now? Well, the capacity of knapsack will be given by j minus weight of I, since ith item is something which we have put into the knapsack. Or the other thing is, it might be possible that without putting the ith item into the knapsack, we will be able to obtain maximum value, in which case the recursion will be dp of I minus 1, since the ith item we are not putting it into the knapsack, so dp of I minus 1 comma j. So the maximum between these two will go into dp of I comma j. And let us say it is not possible to put the ith item into the knapsack, in which case dp of I comma j will be equals to dp of I minus 1 comma j. And in this way, we will be able to populate our dp table, and towards the end we can return the last value of the dp matrix. So that's the discussion of solution, folks. Now let us see how we have implemented this in Python and C++. So first, let us look at the Python implementation. So for this, we have a dp table of size where row is equals to the number of items and columns is equals to the capacity of knapsack. Then we are iterating on I and j. If I equals to 0 or j equals to 0, then dp of I comma j will be equals to 0. Otherwise, if we are able to put the ith item into the knapsack, then we are computing the max between these values, and that value will go into our dp of I comma j. Otherwise, dp of I comma j is equals to dp of I minus 1 comma j. And towards the end, we are returning the last value of the dp table. So that's the Python implementation of this, folks. Now let us submit our solution. So our Python solution got accepted. Now let us look at our C++ solution. So the C++ solution is also the same, folks. We have a DP table, then we are iterating on the DP table and updating our DP of I, j. And towards the end, we are returning the last entry of our DP table. So that's the C++ implementation, folks. Now let us submit our solution. So our C++ solution also got accepted. That is all from this video, folks. In case if you have any question or comment regarding this video, please feel free to use the comment section and I'll try to address them. Thank you.